Module 10, DNP3 Implementation Considerations and Operational Best Practices. 10.1 Purpose of Implementation, Discipline in DNP3 Systems. DNP3 is a deterministic, standards-driven protocol, but system behavior is ultimately shaped by implementation choices. Improper configuration, inconsistent interpretation of optional features, or poor architectural alignment can undermine reliability, performance, and interoperability, even when the protocol itself is correctly implemented. This module addresses implementation-level realities that determine whether a DNP3 system operates as a robust utility-grade platform or degrades into an unstable integration layer. 10.2 Master and Outstation Role Configuration. Explicit role definition. Every DNP3 device must be explicitly configured as master, outstation, dual role, submaster, or concentrator. Role ambiguity leads to undefined communication patterns and must be avoided. Address planning. Each device must have a unique DNP3 address within its communication domain, clearly defined upstream and downstream peers. Address reuse or overlap introduces non-deterministic behavior and must be prevented through centralized address management. 10.3 Point database design and mapping. Logical consistency outstation point databases must be designed with stable index assignments, clear separation of data types, predictable index ranges. Changing point indices after deployment can break master mappings and historical data continuity. Master database alignment. Masters must mirror outstation point definitions accurately. Object groups and variations must match. Index ranges must align. Scaling in units must be consistent. Mismatches lead to silent data misinterpretation rather than protocol-level errors. Number 10.4 Object group and variation selection. Variation strategy. While DNP3 supports multiple variations per object group, implementations must select a primary variation for each data type. Use alternate variations only when operationally justified. Frequent variation switching increases parsing complexity and testing burden. Minimal required support devices must support at least the simplest mandatory variations defined by the recommended protocol subset to ensure interoperability. 10.5 Event configuration and deadband management. Event generation control. Improper event configuration is a leading cause of performance issues. Event parameters must be engineered to capture meaningful changes, avoid excessive event churn, preserve buffer capacity. Deadband engineering. Analog deadbands must be large enough to suppress noise, small enough to capture operationally relevant changes. Deadband misconfiguration either floods communication channels or suppresses critical information. 10.6 Polling strategy design. Class-based polling. Effective polling strategies prioritize frequent polling of Class 1 events, moderate polling of Class 2 events, infrequent polling of Class 3 events, occasional integrity polls. Polling intervals must be aligned with system scale and bandwidth availability. Integrity poll frequency. Integrity polls should be performed at startup, scheduled periodically but infrequently, triggered after communication outages. Overuse of integrity polls degrades system performance. 10.7 Control operation engineering. Select before operate enforcement. For critical controls, SBO must be enforced, select timeouts must be tuned, control reservation behavior must be tested. Disabling SBO for critical operations introduces unacceptable risk. Control feedback validation. Masters must always validate command acceptance, execution success, failure reasons. Control execution without verification violates deterministic control principles. 10.8 Time synchronization practices. Clock alignment importance. Accurate timestamps are essential for sequence of events analysis, fault reconstruction, regulatory reporting. Time synchronization must be treated as a core operational function. Synchronization strategy. Time sync operations must account for communication latency, outstation processing delays, clock drift rates. Periodic resynchronization is required to maintain temporal integrity. 10.9 Buffer management and recovery planning. Event buffer sizing. Outstation event buffers must be sized to survive communication outages, preserve all critical events, prevent premature data loss. Buffer overflow behavior must be explicitly understood and tested. Shaft recovery sequences. After outages, masters should perform event polling until buffers are drained, integrity polls to reconcile state, time resynchronization. This sequence restores database consistency deterministically. 10.10 Unsolicited reporting configuration. Controlled enablement. Unsolicited reporting must be explicitly enabled by the master, restricted to appropriate event classes, monitored for confirmation failures. Improper unsolicited configuration can destabilize shared networks. Fail-safe behavior outstations must revert to safe behavior if unsolicited confirmations fail, communication becomes unstable. Buffered reporting must resume under master control. 10.11 Performance tuning parameters. Fragment size selection. Fragment size impacts throughput, retransmission cost, reliability in noisy environments. Smaller fragments improve reliability, larger fragments improve efficiency. Timeout and retry configuration. Timeouts and retries must be long enough to accommodate latency, short enough to detect failures promptly. Aggressive retry strategies can amplify network congestion. 10.12 Security implementation. Protocol scope discipline, DNP3 provides operational determinism, not full security enforcement. Implementations must ensure protocol access is restricted by network controls. Control operations are authorized externally. Monitoring detects anomalous behavior. Security must be layered around DNP3, not assumed within it. Numbers 10.13 Testing and validation practices. Factory acceptance testing, FAT. Testing must validate object mapping correctness, event behavior, control execution paths, error handling. Site acceptance testing, SAT. Field testing must verify communication reliability, recovery after outages, timing behavior under load. Testing must reflect real operating conditions. Number 10.14 Long-term maintainability considerations. Change management. Any change to point definitions, object variations, polling strategies, control behavior must be treated as a system-level change, not a local adjustment. Documentation discipline. Accurate documentation of addressing schemes, point mappings, event configurations, control logic is essential for long-term system stability. 10.15 Summary of implementation discipline. Successful DNP3 systems are not defined solely by protocol compliance, but by engineering rigor. Correct implementation ensures deterministic behavior, predictable performance, safe control execution, long-term interoperability. DNP3 rewards disciplined design and punishes casual configuration. When implemented with precision, it remains one of the most reliable and durable communication foundations in utility automation environments. Module 11, DNP3 in Long Lifecycle Utility Systems, Scalability, Longevity, and Operational Evolution. 11.1 Utility Systems as Long Lifecycle Engineering Assets. Electric utility automation systems are designed for operational lifespans measured in decades, not years. Unlike enterprise IT systems that refresh rapidly, SCADA, substation automation, and field communication infrastructures must remain functional, interoperable, and supportable across multiple generations of hardware, evolving operational requirements, changing communication media, organizational and vendor transitions. DNP3's architecture directly reflects this reality. Number 11.2 Backward compatibility as a design constraint. Compatibility as a non-negotiable requirement. DNP3 evolution is governed by a strict principle. Open quote, new functionality must not break existing deployments. Close quote. This constraint ensures that older outstations can communicate with newer masters. New devices can be introduced into legacy systems. Field equipment does not require wholesale replacement. Backward compatibility is preserved through additive enhancement, never behavioral redefinition. Practical consequences. Core object groups and variations remain stable. Function code semantics do not change. Deprecated features are retained for interoperability. This allows mixed generation systems to operate reliably. 11.3 Scalability across system size and complexity. Horizontal scalability. DNP3 scales horizontally by supporting thousands of outstations per master, hierarchical submaster architectures, data concentrators, and aggregation layers. Scaling does not alter protocol behavior, only polling strategy, architecture, and resource sizing. Vertical scalability. DNP3 also scales vertically, from simple telemetry devices to complex protection relays and automation controllers. This is enabled through implementation levels, optional features, and modular object support. 11.4 Evolution of communication media without protocol change. Media abstraction. DNP3 deliberately isolates protocol behavior from physical transport. As a result, utilities have migrated DNP3 across dedicated serial lines, multi-drop radio systems, fiber optic networks, Ethernet LANs, IP-based WANs without changing application layer logic. Migration without disruption. This abstraction allows gradual network modernization, parallel operation of old and new media, phased upgrades without downtime. Protocol stability enables infrastructure evolution rather than forcing replacement. Number 11.5 Managing mixed-generation device populations. Real-world deployment reality. Utility systems frequently contain devices deployed 20 to 30 years apart, different firmware revisions, varying levels of DNP3 support. DNP3 is engineered to tolerate this heterogeneity. Negotiated capability model. Masters adapt behavior based on supported object groups and variations, event reporting capabilities, control model support. Unsupported requests result in explicit exceptions, not undefined behavior. NAT 11.6 Database stability and historical continuity. Importance of stable point definitions. Long-term system operation depends on consistent point indexing, stable object definitions, predictable data semantics. Changing point definitions disrupts historical trending, regulatory reporting, analytics, and planning systems. DNP3's data model encourages stable logical identity over time. NASH 11.7 Event data as an evolutionary mechanism. Event-driven efficiency at scale. As systems grow, polling all static data becomes impractical. DNP3's event model allows incremental data acquisition, reduced bandwidth usage, faster operational awareness. Event buffering ensures scalability without data loss. Event strategy evolution. Utilities often evolve from heavy integrity polling to event-centric operation without altering protocol fundamentals. 11.8 Operational change without protocol redesign. Supporting new use cases. DNP3 has supported new operational needs such as distribution automation, fault isolation and restoration, advanced monitoring, centralized analytics without introducing incompatible protocol versions. Extensibility through objects. New functionality is introduced through additional object groups, new variations, optional function usage. Existing devices remain unaffected unless they opt into new features. NUB 11.9 Vendor independence over decades. Avoidance of vendor lock-in. DNP3 enables utilities to replace vendors incrementally, introduce competitive procurement, avoid proprietary protocol dependencies. This independence is critical over multi-decade system life cycles. Sustained multi-vendor interoperability. Devices from different eras and vendors interoperate through standardized semantics, recommended protocol subsets, strict compliance expectations. This preserves engineering investment. 11.10 Operational stability. Under organizational change. Utility organizations change over time. Personnel turnover, mergers and acquisitions, outsourcing of operations. DNP3's deterministic behavior and explicit semantics reduce dependency on tribal knowledge and undocumented behavior. 11.11 Maintenance and lifecycle cost control. Cost drivers in long-term systems. The dominant costs in utility automation are integration engineering, maintenance and support, system upgrades. DNP3 reduces these costs by minimizing custom protocol development, vendor-specific retraining, integration rework. Predictable maintenance model. Stable protocol behavior allows repeatable testing, reusable engineering practices, long-term documentation validity. Number 11.12 Protocol durability versus technology trends. While technologies evolve rapidly, DNP3 remains stable because it solves a narrow, well-defined problem. It avoids unnecessary complexity. It prioritizes determinism over novelty. This restraint is key to its longevity. 11.13 Strategic role of DNP3 in utility modernization. DNP3 functions as a continuity layer across generations, a bridge between legacy and modern systems, a stable operational core amid technological change. It allows utilities to modernize infrastructure without destabilizing operations. Number 11.14 Summary. Why DNP3 endures. DNP3 endures not because it is the newest protocol, but because it is fit for purpose in long lifecycle utility environments. Its longevity is rooted in backward compatibility discipline, transport independence, scalable architecture, explicit semantics, vendor neutrality. These characteristics ensure that DNP3 remains a foundational communication protocol for utility automation systems operating across decades of technological evolution.